yesterday we had spoken about random variables, their distribution functions, their density functions. We have not gone into too much detail because we expect that you can look it up in any standard probability book. So again just I want to recollect that distribution functions are essentially tools which allow you to view the range of the random variable, that is the whole idea. And density functions, especially for continuous random variable, allows you to calculate the probability. And let us now mention that certain random variables can behave in a certain typical way, that is they can follow a certain type of distribution function, that is their distribution function would be actually known, means you can actually know the form of the distribution function. Most of you who have done some basic probability in your basic engineering courses would know that there is a famous distribution for a random variable to follow is the normal distribution, sometimes called the Gaussian distribution. So one mathematician had told me that being a mathematician I should always call it to be a Gaussian variable, but I somehow want to, I always like to say that x follows a normal distribution with mean, mu and variance sigma square. So this distribution has a density function of this form. So this is a very famous one, and you know that the expectation of x or the mean value is mu and the variance. So please remember our aim is not to teach you very basic probability and statistics. You have, I am sure there are a lot of courses in MOOC which a couple of courses which will do that. Our aim is to very quickly with the very basic introduction to take you to the mathematics or probabilistic tools that are required for finance. Our aim is not just knowing probability theory, then we should not have reached this point in this few lectures. So what is our next step? Our next step is to learn this very important lemma called Chebyshev's lemma, and then learn the Borel-Cantelli lemma. These two lemmas are useful throughout, they will be used throughout, because they actually try to look at the behavior of sequences of events, and sequences of events are very important when you talk about finance. So let us write down the Chebyshev's lemma. So x is a random variable. So we obviously distinguish random variable from a random vector. We have just given a definition of random vector in the last class, but we will just essentially consider random variable, that is from x is from omega to r. So let this be a random variable, and p is a number which is lying between plus 1 and plus infinity. Then the probability, see a lot of things about mathematics is actually estimating certain quantities which you can't calculate. So essentially this tells you how to estimate probability if you know, if you can find an average, right. So it tells you that, so if you take the modulus of the random variable, that is basically you are essentially talking about non-negativity here, and this is bigger than equal to lambda, where lambda then for any lambda greater than 0, the fact the set of all omegas for which the modulus or absolute value of x omega is bigger than or equal to this positive quantity lambda, this probability is always less than whatever p you choose between 1 to infinity, does not matter. You will always have this to be true. This is called the Chebyshev's lemma. Now, how do you prove it? The proof is very, very simple. So, let me denote in short this set, which is the set of all such that actually greater than equal to so whenever I write this, I am actually meaning this, that has to be kept in mind. Now, how do I formalize the steps? So, again if I go by the standard definitions which we have already given in the last class, and this is nothing but integral. Of course, everything can be written in terms of the distribution function, which you know, but here we are writing it in the more compact integral or measured theoretic form. This, a whole is obviously bigger than the part. So, this is so in general either, so if I consider the omegas just for this set, obviously these are a subset of this. So, the integral would be smaller because you are talking about non-negative functions. So, this would be but observe that what does this mean, because on this particular set mod of x omega is always bigger than lambda. So, he will be greater than equal to lambda. So, greater than equal to lambda to the power p, because here I have raised the modulus of x to the power of p. So, what I would finally get from here is again I have to put the greater than equal to notation. So, I will have lambda to the power p So, what does this mean? This simply means the probability of this particular event, probability of this event. So, this is nothing but lambda to the power p probability of, and you see voila, you have proved the Chebyshev's inequality. Of course, Chebyshev's inequality will have applications which we will come very soon. Another interesting idea that we will come to is the Borel-Cantelli Lemmas. So, we are going to now talk about what is the meaning of the notion of a sample point occurring infinitely often in a given sequence of events. So, if there is a sequence of events say 1 a 2 dot 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 a n, the question is that if I have say omega element of the sample space, what is the probability or what does it mean by telling that this omega occurs infinitely often in this sequence, right. So, what we will first do is to consider a probability space, and then I will consider a sequence a n where each a n belongs to u, and then I will write this, I will construct, make this construction. I will fix up a value of n and then take m is equal to n to infinity, and then I will change and then I will shift the n. So, I will say I will take n equal to 1, then I will take n equal 1 to infinity. So, I will take the union of all the events here, then sorry I made a mistake, this is the intersection. So, what I am going to do, first I will take say n equal to 1, so take the union of all things, union of all the sets here. Then I will take out A1 from there, so I will start from A2 to AM, I will take the union of that and keep on doing it and then try to find a common intersection, right. This thing is often written as follows. So, what sort of final set it consists of? Now, this is an element of the question is this an element of the sigma algebra? So, once you take the union, is in the sigma algebra, all those unions are basically what you are taking the unions. So, each of the union are in the sigma algebra. If you have countable union in the sigma algebra, then you know that the countable intersection are also in the sigma algebra, right, because you can take the de Moivre's law. So, this set is actually an element of the sigma algebra. So, this is what sort of sample points are here. So, this is all those things where omega belongs to infinitely many ANs. So, what does this mean, belonging to infinitely many ANs? So, it might belong to A1, then A3, then A5, then A6, then A7, then A8, and A9, and then say from A100 to A101 and just goes on, something like this. Suppose 1 omega belongs to A1 and A2, nothing else, it does not come anywhere, then we do not consider it here. This is sometimes written as, this set is also sometimes written as, because it satisfies the type of things that we do with actual sequences of real numbers. It looks almost similar to that. I will allow you to ponder over what I am writing here, whether it makes sense intuitively to call it a lim sup of AN. So, we also call it this. What Borel-Cantelli Lemmas says it gives you a more fascinating proposition. It says that now okay, each of these PANs, if this is there, if this is, then this is a null event. This is a null event, that is beautiful. And it says if your probabilities have a finite sum, this infinite series, then this event must be a null event. It is a huge conclusion you are drawing. That is, there is no omega which will belong to infinitely many ANs. If it at all the omegas will belong to some finitely many ANs. That is a huge conclusion. Sometimes you write this set also as, some authors also write AN infinitely often. So, this is a symbolism of this, it does not mean anything. So, I will just use this shortcut symbol. So, omega belongs to AN. So, what would happen, that there will be some AN in which there will be infinite number of omegas coming in, that is the key idea here. Okay, do not bother about this much, just you are essentially constructing a set where omega belongs to infinitely many ANs, and we are trying to find the probability of this. These type of sets become very important when we will study the central limit theorems. So, we will not do much proofs there, but we will give you a hint of what can happen. And so, let us draw the conclusion. So, if this happens, it tells you that probability an IO, which is same as adding the lim sup this thing, is 0, that this is a null set, empty set, there is no omega which belongs to infinitely many ans. Okay. So, how do you prove this? Proof is very simple. So, if you look at this set, so let me take some n and look at this union m equal to n to infinity, say n equal to 3, say m equal to 3 to infinity. So, that set is one of the sets. So, if you have A1 intersection A2, so the intersection must be smaller, must be a subset of either A1 or A2, it is a subset of both. So, if I take any n, it does not matter, this whole thing is a subset of union m equal to n to infinity, because what I am trying to say is that this whole, that is an IO, is a subset of, for some n, whatever n you choose, not for some n, all n actually, whatever n you choose does not matter, this is always true. So, if that is true, which will immediately tell you that the probability, of course, the larger set would have a larger event, or event which has more possibilities of occurrence will have a larger probability. But what does this mean? This again means, by very Kolmogorov axioms, but if I look at this, what is this? This is a tail of a sequence, tail of, or rather a tail of a series, summation p a and n equal to 1 to infinity is the tail of the series. That is, we are shutting off finite amount of elements, cutting off finite number of terms of the series and looking at the remaining part. So, the tail of the series will always go to 0 if this sequence, right, if this sequence actually is strictly less than infinity. If this sequence is convergent, then the tail always goes to. So, this is a notion from infinite series which I expect the viewers of this thing is supposed to know, because that is the sort of requirement that we had, that you have to have some understanding of mathematical analysis. So, now if I look at this one, so what is happening as n tends to infinity, this will go to 0. Now, this is actually a fixed probability, this is a fixed event. So, which means as I take the limit on this side and this side, this remains unaffected by the limit operation, because this is already a fixed set, everything is done. So, which from here, so we will have this, so it will we can conclude now that but anyway probabilities are always greater than or equal to 0, and this will immediately tell me now. Let me show you an application of all these things that we have just spoken. I mean, an application of the Borel-Cantelli lemma, an application of the Chebyshev's theorem, and that comes out if when we are talking about convergence of random variables. If I am using a vector valued random variable or random vector, then if I need to use it, I will make an explicit mention of that. Otherwise, please understand that we are always working with random variables, that is functions which are mapping sample points to real numbers. Now, there is something, there are two types of convergence which are very important. One is convergence in probability, and convergence almost everywhere. So, suppose I have a sequence of random variables x n and I say x n goes to another random variable x, and we say it converges almost surely, almost everywhere convergence. This is called almost everywhere convergence. AS is a short form of the word almost surely. So, when I am talking now, so what these are random variables are functions. So, a sequence of function converging to another function. So, when I would say, when can I say that, what is the meaning of a sequence of functions converging to another function? It means, technically it should mean that for whatever omega that I have in omega, this is what it should mean if I am talking about pointwise convergence. So, this, if this happens, then this is what is called pointwise convergence. This is what is called pointwise convergence, and then one needs to understand that in probability theory, the tendency is always to throw out null events. So, we say xn tends to x almost surely if probability of the event, that is a collection of all omegas, such that this is not true. Probability that xn omega does not converges to omega, the collection of all such omegas is a null event. There can be some omegas in omega for which omega in the sample point for which this may not happen, but their collection would form a set whose probability would be 0. If that happens, then we say xn converges to x almost surely. And then there is the notion called convergence in probability. We will see how these are connected. Convergence in probability. So, what is the meaning of convergence in probability? Let us discuss this little fact. We will take 10 more minutes to finish everything. So, let me discuss this little fact, convergence in probability. So, convergence in probability means we say xn converges to x in probability if so we are telling that the set of all omegas for any given epsilon, take any epsilon, if the set of all omegas, so this is the probability that the set of all omegas such that the distance between xn and x is strictly greater than epsilon. Then if as you keep on increasing the value of n, right, suppose I say x1 minus x strictly greater than omega, so I collect all those omegas, that has a probability. So, you have x2 minus x strictly greater than epsilon, there could be some omegas where for which that is true, so that will have a positive probability. But then as I increase the value of n, this should go to 0, that this distance cannot be bounded away from 0, that there cannot be positive number such that this distance would be always greater than the positive number. So, that the fact that that probability in the limit, the probability that this distance is bigger than some epsilon would be 0. So, you are expected to xn is expected to be coming towards x, that is the whole idea, that sort of explanation one might think. Of course, every I mean, if you are satisfying this, you are satisfying that, but there is an interesting thing that okay, if I am converging in probability, am I converging also almost surely? So, if I am converging almost surely, I leave it to the listeners or viewers to decide whether they converge in probability. The answer is yes. Now, the question is, if I am converging in probability, am I is the same sequence also converging almost surely? The answer is there is at least a subsequence which is converging almost surely to the same random variable. So, this is a theorem, if you want to write it like this, if xk converges to x in probability, then there exists a subsequence xkj of x xkj, which is a subsequence of xk, such that this subsequence converges almost surely to x. Now, this definition of probability, you must understand that this should be true for all epsilon greater than 0. Whatever we have chosen epsilon, this will always happen. It does not matter for some epsilon this will not happen. This has to happen for all epsilon. So, that is something you have to keep in mind when you are talking about convergence in probability. So, what does it mean? So, how do I prove this? So, idea is that you take any integer j, does not matter whatever integer you are taking, take any integer j. We can always select a kj or a index value so large that this difference, the fact that the probability that the difference between xkj and x is bigger than some 1 by j square or 1 by j something like this, can be made smaller than some quantity. So, the idea is that for each, why can we make it as smaller as I like? Because I have this fact, because I know that it converges in probability, that this, what does this mean? This simply means that when n is large, this probability can be made as small as I like, can be made smaller than some delta, right. So, given for each j in n, we can find kj so large, because this is where we are exactly applying the fact that we are talking about, the fact that xn tends to x in probability, that definition we are now applying. So, for each j we can find a kj so large that probability of xkj minus x, this is bigger than 1 by j, this is my some sort of an epsilon, this is less than some delta, that delta may be chosen as 1 by j square. So, I can find a kj, if this is my delta, I can always find a kj for which this is bigger, is less than 1 by j square. This is exactly I am applying this definition, because this holds for whatever epsilon I want. So, once I have done that, you might note that I can always choose k1 less than k2 less than kj minus 1, because we are essentially taking a larger and larger kj. So, this can always be done. These are very simple techniques in analysis, mathematical analysis, which mathematicians use. So, I am essentially giving a small warning, even to make money you need to know some good mathematics, though many mathematicians do not have money. but now let me try to show you what does it mean. Now let me construct. So what you are constructing? You are always taking an increasing kj. So this kj is actually going to infinity. So you are increasing j. As you increase j, you increase the kj, right? So this is the increasing function kj, increasing function of j. This is exactly the definition of a subsequence. Because in subsequence, when you choose the nk or kj, you are actually constructing an increasing function. That's increasing function of the indexes. Because you have to maintain the order. That's the meaning of a subsequence. Now you construct, let us construct these sequences, this events. The set of all omega in omega such that x kj omega minus x omega is strictly bigger than 1 by j. So I am looking at all such for every j equal to 1, 2, 3, 4, I am just trying to figure out. So for given a j, this should happen. So find for every kj, take the kj and put that particular j as this aj index it with the same j. So here I have an infinite sequence of events. Now I know that probability of all of them is strictly less than 1 by j square. So if I sum it up from j equal to 1 to infinity, the probability is strictly less than infinity because summation 1 by j square is a convergent series, right. So here I will get, since summation 1 by j square is strictly less than infinity, it simply tells me that probability and this is a place where you apply the Borel-Cantelli lemma. So what does the Borel-Cantelli lemma says? That this thing, this would imply that probability aj infinitely often is 0. Sample points omega do not occur infinitely often. So what does this mean? That is for almost all sample points except a few of them. For almost all sample points, what do I have? So here is something we now have to look into. So for almost all sample points, we have so this probability is 0. So for almost all sample points, this has to be true. So omega cannot be occurring at infinite many ages. So for infinitely many omegas, the opposite must occur. For infinitely many omegas, this will not occur, only the opposite will occur. So what does this mean? Where j is in some greater than some particular j, some index depending on the omega, does not matter. So what does this mean? This simply means that xkj goes to x in probability. This simply means that xkj omega minus x omega can be made as small as I like as j is increased. What does it mean? But this is not true for every omega, for almost all sample points omega. This simply means that xkj goes to x almost surely. So, with these ideas, and I would like to stop my discussion here, and tomorrow we will see that how these ideas can be used, for example, to talk about central limit theorems and law of large numbers, which are actually very useful while you study Brownian motion, and Brownian motion is central to understanding the flow of stock markets. And also the Ito calculus depends on Brownian motion. Ito calculus is the calculus of computing the derivative pricing, the derivatives. So, let us stop here and let us see tomorrow what we can discuss about central limit theorems. Thank you very much.